Hello everyone, welcome to this next video on classical mechanics. In this video we shall be seeing Hamiltonian's variational principle and its relation to Lagrange equation. So now can you see this pendulum? In this pendulum I have this bob over here and it is attached by this string to this rigid support over here. So now this is the initial position for this pendulum, and I can now move this pendulum over to this position. Now at this position, this pendulum can take various paths and it can have various oscillations depending on in which direction I release this bob. If I release this bob, so it will tend to go in this direction, and if I pull the bob towards myself and then release it, it will go with this direction, and if I push it a little backward, in that case it will go in this direction. So you see this pendulum can have many paths, and so similar to this pendulum we have in other mechanical system. The tendency of any mechanical system is to follow the shortest path, which would take the lesser amount of time. And this path is usually known as extremum. That means it would take the minimum possible path for it. The word extremum, it means we are either talking about minimum or we are talking about maximum. So the motion of any mechanical system is defined using this action. And what is this? It is a functional which is defined as integration from t1 to t2 L dt, where what is this L? L is again a function of the generalized coordinates and generalized velocities and time. So this L basically is a function of qj's, the generalized coordinates, qj dots, the generalized velocities, and the independent variable time. And this L, the Lagrange, it is calculated by taking the difference of kinetic energy and potential energy. So this action is defined, and this action has to be minimized. You'll see in a moment how. Before that, let us first differentiate between this conservative system and non-conservative system. In the previous video, I have discussed about conservative system, a system in which total mechanical energy of the system remains conserved, and in non-conservative system, this energy do not remain conserved. That means we also have some frictional forces and dissipative forces acting on the system. Moreover, the forces in the conservative system, they are derived from the potential function, which are ordinary in nature and not generalized. Whereas in non-conservative system, these forces, they are derived from generalized potentials, which are also a function of velocity dependent, And in this case, the potential or the potential energy V, this is purely a function of generalized coordinates. That means V only depends upon Q and not Q dot. But here, so in this case, if you take the derivative of V with respect to Q dot, as it does not depend on Q dot, it would come out to be 0. But in this case, V is a function of both the generalized coordinates as well as the generalized velocities. So now, as we were talking about what path does any system would follow naturally, this pendulum, it will tend to go by this straight line path, or you can say in this path, because it is the shortest possible path. So this Hamiltonian's variational principle, what does it say? It says that the motion of a system from moving from time t1 to time t2 is such that the action defined by this functional, this gives you an extreme value for the path of motion, and this extreme value, that would be the path which that object or that mechanical system would follow. So this describes the motion for any conserved mechanical system. And we have another definition for this Hamilton's variation principle. It says that the variation of this action, the quantity action, this delta, it represents variation of this action. It is 0. So, and this is known as the principle of least action. You can relate this thing to calculus of variation, as in calculus of variation we know the necessary condition for any differentiable functional to have an extremum is that its variation should vanish. So here also you see, for this functional to have an extreme value, its variation should vanish. So these statements are both true together. So now let's move on to calculate this functional. So we'll take the variation of this action and put it equal to 0. So our action was this thing. Now L is a function of generalized coordinates as well as generalized velocities. So when you differentiate this, you will get, now L, this is a function of q1, q2 up to qn, and this is also a function of q1 dot up to qn dot. So when you take its partial derivative with respect to time, or simply, then you will get del L by del q1 into the variation of del 1 of q1 plus del L by del q2 into the variation of q2, and so on. We have del L by del qn and its variation with respect to qn, and then we can take the derivative with respect to these coordinates, the partial derivative with respect to these coordinates. So it would give you these values, right? Del L by del qn dot and then the variation in qn dot. So summing these quantities, over here we have this first summand and the second, these quantities into this summand. So let us substitute this value of variation over here. So we have this expression, right? So now we can separate the terms. The first terms come here as such. For the second term, we can integrate it term by term because there's this derivative variation of this generalized velocities, and we wanted to get rid of this dot, so we have to integrate it. So we can consider this to be the first function, this to be the second function. So you see, integrating it by parts, we have first function as such, and then the the integration of this function, that would give you the variation of qj only and not qj dot, and substituting the limits from t1 to t2 minus integration derivative of our first function, and then the integration of second as such. So here it would be del L by del qj dot, right? So we have this thing, this is equal to 0. So now, because we have fixed the coordinates at the end points, therefore this variation at both the time interval, initial time interval and final time interval, that gives no variation, so it is equal to 0. So overall this quantity, it becomes 0 because of this factor. So we are only left with these quantities, these two quantities, and we can take this variation of qj common, so we'll have this expression. Now all these qj, they are independent to each other by virtue of the definition of generalized coordinates. Therefore this coefficients, these are equal to 0, because if you have some three vectors, say a, b, c, and they are linearly independent to each other, that means we can find three scalars, say capital A, capital B and capital C, such that if you have capital A into small a plus capital B into small b plus capital C into small c equal to 0, it implies A equals to B equals to C, they are equal to 0. From this condition, we can have these coefficients equal to 0. And how many such coefficients are there? There are n such coefficients. So we have n equations of such kind. Now these equations, they are known as the Lagrange equation of motion. Now let us discuss, one should remember these equations. And now let us discuss several cases. The first one is for conservative system. In conservative system, we have L is equal to T minus V, where T is the kinetic energy and V is the potential energy everywhere. But for conservative system, this potential energy, this is a function of Q only and not Q dot. That means this derivative, this term is equal to 0 in conservative system. So let us substitute the value of L over here as T minus V. So we, instead of L, we write T minus V here and here. Then we can separate out the terms. From the first one, you'll get del T by del Qj, and from the second one, you'll get minus del V by del Qj, and similarly on the right hand side. So now you see this quantity, this is equal to 0 because our potential is independent of Qj dot. Therefore, we are only left with this term. So this term on the right hand side, minus del V by del Qj, this is known as the generalized force when our system is conservative. Therefore, we can replace it by this. So for conservative system, you should remember this form of Lagrange equation, because here T is kinetic energy and this Qj, that is the generalized force associated with the system. So now for the non-conservative case, again we have L is equal to T minus V, but now V here is the generalized potential and it depends upon the generalized coordinates and generalized velocities, the derivative of generalized coordinates. So in this case, this quantity is not equal to 0. Therefore, we have, while substituting the value of L over here, we have T minus V instead of this. So solving this and shifting all the T quantities to the left and V quantities to the right, this whole terms is termed as Qj, where what is this Qj? Qj is the generalized force. So one should remember this equation when the system is non-conservative. So you saw in Lagrange equation of motion, we have the concept of energies, the associated kinetic energies and potential energies. But in Newton laws, we have the definition of force as mass into acceleration. So here forces are used to define the motion, and whereas in Lagrange equations, we have energies which define the system. So therefore, this Lagrange, this is purely a scalar quantity, whereas Newton's equation include force, therefore that would be a vector quantity. And Lagrange approach is easier to solve and it is general for any system. This formulation is generalized because we use the generalized coordinates instead of any particular kind of coordinate system for any specific problem. So this concept is more general as in the sense of Newton's approach. The third case is a system involving non-potential forces. In conservative system, we saw the potential force component F, that is available from velocity independent ordinary potential, though that would be a function of ordinary potential. And in non-conservative system, this potential force component is velocity dependent generalized potential. But there are also some forces which are not derived from potential function. For example, Coriolis force or Lorentz force. In Coriolis force, you see, this appeared due to rotational motion and it's found in many rotational things, whereas this Lorentz force, you find this on a charged particle which is moving in a magnetic field. So in such kind of forces, they are not derived from any kind of potential. That means they are not a function of potential V. So for that, we can denote the non-potential force by this Qj dash. So the Lagrange equation of motion, they simply become, this thing is equal to minus Qj dash, where Qj dash, that is a function of generalized coordinates and generalized velocities and the variable time. So this is a more general sense when the force corresponding potential force that is not depending upon potential. So these forces are known as non-potential forces, and such systems are non-potential system systems with non-potential forces. So in this video we saw Hamilton's principle, that is both a necessary and sufficient condition for Lagrange equation of motion. And in the next coming videos we shall see various applications of Lagrange equation. Well, that is it for this video. Thank you for watching.